This is the second part of the video over section 6.2. In the first video, we took a look at finding the volume of solids where all the cross sections were the same shape, but of different sizes. In this second video, we're going to be taking a look at what are called volumes of revolution, where we take a curve, some curve that is non-negative, and we revolve it around a line, either the x-axis, the y-axis, or some other horizontal or vertical line. By revolving this region around the axis, we create a solid, and we're looking for the volume of the solid, not the volume it might hold if it's hollow on the inside, but the volume of material needed to make the solid. Let's go ahead and talk about what it might look like and how it might be formed. If the curve touches the axis of rotation, then the three-dimensional object will be solid on the inside. If the area being rotated does not touch the axis of rotation, then it will be hollow in this inside, sort of like a vase. It's our task to find that volume of material needed to make the object. Let's take a look at a picture so you can see more clearly what might be happening. In the image on the left, you can see that we have a curve. If we take the region for the function between 0 and 9, and we revolve each region about the x-axis, we create the solid that you see over here in the right picture. In other words, if we're rotating this small sliver here, it creates this part that you see here. And this part here, where we have a relative maximum, creates this large bulge that you see here. That bulge is created by the relative maximum. And then you can see this small relative minimum here below, which gives us this, well, sort of nodule type shape that you see on the end. In this case, the area to be rotated does touch the x-axis. So this creation that we have is solid on the inside, will not hold water or any other material. It's completely solid. And our job is to find out how much material is needed to create that shape. So in this video, we discuss these volumes of revolution and how to find the volume using a method called disks or washers. Now, a disk and a washer are not exactly the same thing. When you think about a disk, you're actually thinking about something like this, or like a hockey puck. It is circular here, but it is actually a cylinder because I have a circle of the same size and same shape on both sides. It does have thickness to it, which we call the height of the cylinder. And what we're going to be doing is we're going to be using disks like this in order to approximate the volume of a solid like this one. What we're going to do is we're going to slice the region perpendicular to the axis of rotation. That means, since the axis of rotation here is horizontal, that we'll slice it vertically. In other words, we're just taking a partition of the x-axis. And then we're going to divide it into little rectangles. And we're going to take each rectangle and rotate it about the x-axis. When you do that, it becomes something more or less like this. It's sort of rectangular in shape, and when you rotate it, it creates a disk. In other words, a circular cylinder with a certain amount of thickness to it. This thickness is, of course, the differential, in this case, dx. Let's take a look now at a picture of what this might look like. You can see here the shape of the original graph. You can also tell that the interval over which we are revolving has been divided into some subintervals. These partitions create a differential dx or delta x. That's the width, or in fact, the height of the cylinder. The cylinder is created by taking one of these rectangles and rotating it completely around the x-axis to create a shape like this, which extends outward from the plane view of the image. In this case, what we can do is we can use the formula for the volume of a circular cylinder, area of the base times the height, in order to approximate the volume of each partition. And we add the partitions together, and of course, we take the limit as the number of partitions goes to infinity. This should give us the volume of the region. Now, this happens when the graph touches the axis of revolution. It creates this solid disk. What happens, on the other hand, if instead it does not touch the axis of revolution? Let's think about what might occur. When it doesn't touch the axis of revolution, such as this particular shape right here, and we want to revolve it around the x-axis, notice that none of these little rectangles, our partitions, actually touch the axis of rotation. What we end up getting is actually sort of two surfaces, an outer and an inner. The outer created by the curve that's farthest away from the axis of rotation, and an inner surface created by the curve that's closest to the axis of rotation. What it creates is an object with a cavity on the inside, something that's hollow in the middle. Because this shape doesn't touch the axis of rotation at any point, it's actually hollow all the way through. You can see on the interior here that there is a red, well, washer-shaped object. And that is, in fact, what we do call it. We call it a washer, much like the thing that you put inside of your faucet to keep it from leaking. So it's one of these shapes right here. You can also think of it as sort of a ring shape, like this one here. It is still a cylinder, but we've cut out the middle part. So in fact, when we rotate, we get what's called this ring, or an annulus, annuli for plural. We're going to have to figure out how we can divide up the regions, find the volume of each partition, and combine them together. And I know you know that this sounds like a definite integral. It will be the limit of a Riemann sum. Our learning objectives are to find the volume of a solid of revolution using the disk method, where the disk is the solid circular cylinder. This happens when it touches the axis of revolution. And then to find the volume of a solid of revolution with a cavity in the middle, like this one, when the area to be revolved does not touch the axis of revolution. Now, keep in mind, what we rotated around completely changes the object. If I were to take this same area and rotate around the y-axis, because it touches the y-axis, it would not have a cavity on the inside, and it would not look remotely like that. It would instead resemble a vase. We're going to explore in this video how we can do this. Now, before you freak out at the length of the lecture notes, I will tell you that most of the lecture notes are pictures like the ones you see here. There's actually not that much text in the lecture notes, but I did include a lot of pictures to help you understand what's happening. Volumes of revolution are a very common application of calculus to apply. However, I will tell you that some students are better able to see what the revolved shape will look like than others. If you are under age 25, you may find that this is difficult for you. This ability to predict the three-dimensional shape is one of the last things that develops in the brain in late adolescence. And adolescence in this case means neurologically. which occurs from about age 15 to about age 25. So your brain is still growing and developing at a rapid rate until you reach around age 25. And if you're 18, 19 years old, you may struggle with predicting what this will look like when revolved around the x-axis, simply because your brain hasn't developed that spatial awareness yet. But don't worry, I have some tools to help you out. Let's take a minute and just practice predicting what it looks like. Keep in mind that if we're taking something like this shape right here, and I'll move it forward so you can see it, if I were to revolve it, what do you suppose it would look like? Again, imagine taking a partition and revolving the partition. It creates that circular cylinder. If we revolve the whole thing, and I'll have to take my paper clips out if I can. If I were to revolve the whole thing, some of you may have already recognized that what I have in the revolved shape would be a wedding bell. Now let's practice on something that's not cut apart and not quite so difficult to predict. Here is the same shape, but not cut apart. And when you rotate it around its axis of revolution, you do get the wedding bell. Note that this edge is the axis of rotation. What do you suppose this shape might end up being? You can either orient it vertically or horizontally, or actually anywhere in between. It's actually better vertically, and when you rotate it, you get a pineapple. I have one last example to work here, and this is also one that's best done vertically. When you're looking at this one, what do you think it might look like if I were to rotate it around this axis of rotation? In order to imagine what it will look like, take this graph here and create the mirror image of it on this side. That's how we form the full shape. And in this case, it's a baby bottle. Let me go ahead and share my screen with you so we can get started talking about volumes of revolution by disks and washers. I said previously that these volumes of revolution are a common application of calculus, and in fact, they are. You can see in these two pictures here what's called a lathe, L-A-T-H-E. This is a machine that rotates on an axis. And as it rotates, you can create different solids of revolution by having a knife here that carves out different shapes. In this picture here, they're creating the legs to chairs or tables. And in this picture here, they're creating a part that goes inside of a watch. These are an application of a volume of revolution. In order to create this three-dimensional object, you have to program in the shape of the curve that's creating the volume of revolution. Let's now take a look at another picture of volumes of revolution. In this case, we're going to take a non-negative graph, which is typically what we use, though it's not necessary. And we're going to take it and revolve it, in this case, about the x-axis. If you're going to revolve about an axis, it's a good idea to indicate that by drawing a curving arrow around the axis of rotation. That way it reminds you which one you should be reflecting across. In order to see what this looks like, you need to take this image and reflect it at the same distance below the axis of rotation, which is in this case, the x-axis. If you look at this picture in the middle, can you see the shape of the curve at the top of the volume of revolution? And at the bottom, do you see the mirror image of the shape reflected below? Let me highlight the two sides so that you can see them. If I were to highlight this side, I am in fact getting this curve here. On the bottom, however, it's not that curve exactly. It is instead the reflection of the curve across the x-axis. This is the same image, just rotated to show a little bit more of the shape of the solid. Notice that in this case, this area that we are rotating between the curve and the x-axis touches the axis of rotation, the x-axis, which means that this is completely solid. It does not hold water or anything else. It's solid through and through. Let's take a look now at the reflection. In this picture, you can see the upper curve and the lower curve. A good way to actually visualize the object that you're going to get when you revolve is to take a reflection of the curve over the interval that you're going to be revolving. And then sometimes if you connect them with what look like, well, oblong circles, if you connect them like this, you start to get the shape that you'll see over here. This is a good way to learn what it's going to look like when you revolve it. We'll also have technology available to help us out. Here's another example from the textbook. In this case, we're integrating between some value in quadrant 2 to some value in quadrant 1. The curve is non-negative, strictly above the axis, and it touches the axis of rotation, which is again the x-axis. And when you start to revolve it around, you can tell that it's creating this 3D image. Because it touches the axis of rotation, it will be solid all the way through. And you'll end up with a solid that looks like this. Each individual slice that we're going to use to approximate is again a disc, which in many ways kind of resembles a quarter coin or a hockey puck. It is a Coke can, basically, but a very, very short one, where the height of the cylinder is the differential. Let's turn our attention to some of the terminology that we need. We've been talking quite a bit about the axis of rotation. In our case, that's always going to be either the x-axis, the y-axis, or some other vertical or horizontal line. Now, keep in mind that the x-axis is actually given by y equals 0, and it is a horizontal line. And any other horizontal line would be given by y equals c. The y-axis, on the other hand, is given by x equals 0, and any other vertical line would be given by x equals c. We will be revolving around lines that are not one of the coordinate axes. Be sure that you understand how to do that. I always ask it on my exams. The axis of rotation could be slanted or rotated in some other way, but we're not going to look at any of those. All of ours will either be horizontal or vertical lines. For now on, when we talk about a volume of revolution by disks, we're going to be talking about revolving around some line or some vertical line or some horizontal line. We're going to start by rotating around horizontal lines. And the reason for that is relatively straightforward. When you rotate around a horizontal line using the method of disks or washers, remember, the washer is the shape that looks like this. It's called an annulus with a ring in the center, and the disk looks like this. If you're going to revolve around a horizontal line, then your strips, which must go perpendicular to the axis of rotation, have the narrow end along the x-axis. And that makes the differential, which is the height of the cylinder or annulus, the differential dx. So we start with revolving around horizontal lines because it's more what students are used to, integrating with respect to x. We will also look at integrating with respect to y. In that case, as you might imagine, the cylinders are going to go in the horizontal direction because the axis of rotation will be vertical. Let's take a look at this graph here, x minus 1 quantity squared plus 1. You can see that we have a thin rectangle right here drawn between the axis of rotation and the curve. The axis of rotation is the x-axis. This small measurement at the bottom is the differential dx. Notice that when you rotate, this region right here becomes this disk. And when you're looking at the disk and you fit it directly on there, notice that the center of the disk is located right there where it meets the axis of rotation. But that means that the length of the rectangle is actually the radius of the disk. So this right here becomes the radius. But this is given by the y value on the function. Now we know how to find the volume of a right circular cylinder. You take the area of the base, which is a circle, pi r squared, and you multiply by the height, which in our case is the differential dx. This will give us pi r squared dx, but r is given by this function. Now, once we have that, it's a pretty straightforward matter to add them all together and take the limit as the number of partitions goes to infinity. Let's take another look at this same region and what it might look like. They're integrating here from 1 to 3. Again, that's the interval on the x-axis over which they're going to revolve the shape. You have to know which region you're revolving because the solid depends on the region that gets revolved. If you revolve a different region, you'd get an utterly different solid. In this case, it looks kind of like a spool that might hold cable or wire or something like that. And because it touches the axis of rotation, it's completely solid all the way through. We'll need different bits of information in order to write the integral. We will need to know what the volume of one slice is. But as I said, it's going to be pi r squared times the differential dx, where r is typically given by the y value on the function, or the y value on the function plus or minus a constant. Notice also that the strips, the little rectangles, like the partitions in a Riemann sum, are drawn perpendicular to the axis of rotation for the disk and washer method. We will learn in the next section about the shell method, which also finds these volumes of revolution. It's a different technique to find the same thing. In the shell method, however, you draw the rectangles parallel to the axis of rotation. It does not use a disk or a washer to approximate the volume of the solid. Instead, it uses a series of cylindrical shells, just like small pieces of pipe that are hollow on the inside. In that case, when we draw those rectangles, they're parallel. The way to keep it straight is to remember that shell has 2 L's in it, and parallel does as well. So those must be parallel, whereas the disk washer method, they must be perpendicular. Now, we'll also need to know about the limits of integration. The limits of integration are determined by where you are integrating over. In other words, if you're integrating with respect to x, you start with the x-coordinate of the first rectangle and go to the x-coordinate of the last rectangle. The rectangles are very important in finding the different pieces of the definite integral. Most students have a very, very strong bias towards wanting to integrate with respect to x. Even when it's better to integrate with respect to y, they still want to integrate with respect to x. We will learn both methods, but after that, you may find that it is simpler when revolving around a horizontal line to always use the disk or washer method, because if you're revolving around a horizontal line, then the rectangle has to be perpendicular or vertical, and that makes the differential dx. However, if you're going to revolve around a vertical line, you may instead want to use the shell method, because then you would draw the rectangle perpendicular to or parallel to it, in which case the differential would still be dx. In other words, if you revolve around a horizontal line with the disk washer method or around a vertical line with the shell method, you can always integrate with respect to x. Let's take a look now at some different shapes and at some technology that can help us to revolve these things. When we're looking at this, there's a GeoGebra applet that will help you do this, and the link is in the lecture notes. There's also a link to a program called Calc Plot 3D. Calc Plot 3D is probably much better at doing this, and it has some aspects that are super nice for understanding what a volume of revolution is. We'll use Calc Plot 3D extensively. When you get to Calculus 3, you will use Calc Plot 3D on a daily basis. However, in this class, we just touch on it when we do volumes of revolution. If you need some help, I have a handout and you can contact me for that handout. Let's take a look at this graph again, and let's integrate this shape over the interval from 0 to 9. And we're going to revolve around the x-axis. In GeoGebra 3D, you would get this shape right here. It would also give you the volume of that shape. Let's take a look at the applet. In the GeoGebra applet, you enter the function that you wish to revolve in the first box. Then you give the x-coordinate of the first rectangle you want to revolve, the one on the left, in the A equals box. And in the B equals box, you put the location of the last rectangle you want to revolve. In other words, A to B is the interval over which you're revolving the shape. Then you indicate how many rectangles you'd like to use. In this case, I have it set up for 5, but 5 may not be enough. So let's go ahead and change it. We can increase the number of boxes, which will increase the accuracy of the volume. The more boxes, the more closely it resembles the shape of the curve over the interval from A to B. Then there is something here called spin rectangles. When you spin the rectangles, it actually revolves them all the way around. And if you rotate it a little bit, if I can get it to rotate, and it's not rotating the way I want, but okay, you can see the circular discs that become the approximation to the volume. And I believe it gives the volume somewhere. I'm not seeing it at the moment, but usually it does. Let's now take a look at the same curve in Calc Plot 3D. If you want to find Calc Plot 3D, you can Google Calc Plot 3D and it should pop right up. In this case, I have graphed the particular curve. What you look for is in the select box, you want to select surface of revolution, which is the very bottom option. Once it opens, you have the option to write the function as y a function of x or x as a function of y. We'll use both of these today. Then you give the top curve that you're revolving and the bottom. In our case, we want to revolve all the area between the curve and the x-axis. So I use the x-axis, y equals 0 for the bottom. Then I enter that x goes from 0 to 9, and I have to enter what the axis of revolution is because that changes the shape of the solid, which in this case is y equals 0. This slider bar allows us to revolve the washers and shelves. Let me back it up so that you can see a little bit better what it looks like. And I'm going to reduce the number of shells so it won't take so long to draw. I've changed it from 50 back to 14. What I want to do now is rotate it a little bit so you can see it more side on. When you're looking at it from this direction, you should be able to see the original curve right here behind those discs. And when we revolve the whole thing, you can see it all revolving. Let me rotate it back so you can see the side view. Oops. As you unrevolve it, you can see them coming right back around to the curve. Now we can also show what's called a representative triangle, or rectangle rather. The representative rectangle is just one of the partitions, and you can revolve just the representative rectangle, which when it comes around forms a circular disc. And again, you can revolve the whole thing. Down here where it has number of layers or slices, it typically starts with 15 to 40, but if you use a lot of partitions, you may want to increase it to 40 and 40. Let's go ahead and revolve it now, the whole thing, so that we can see all of it. When I've revolved it, I can actually rotate it and look at it from all the different directions. I can also find the estimation of the volume by scrolling up, and it will appear in the upper bar, and it's giving us the approximate volume here. Let's go ahead and make it more clear how they actually computed that volume. Again, they're taking the area that's between the curve and the x-axis, and they're drawing representative rectangles. They're partitioning the x-axis. The strips or rectangles must be perpendicular to the axis of rotation. Because the axis of rotation is horizontal, then the strips must be vertical. This is required for the disk method. This also makes the narrow end of the strips in the x direction, which makes the differential dx. Then, of course, what we do is we rotate. When we rotate one, we get the circular cylinder. And again, if we're looking at the graph, the radius of this circular disk is the height of the function, the distance from the function to the axis of rotation. That's the radius. To find the volume of that, it's a cylinder. So I know that the volume of a cylinder is the area of the circle, pi r squared, times the height of the cylinder, which is our differential dx. In this particular case, I would take pi and the function and square the function, multiply by pi and the differential dx, and integrate from 0 to 9. And you can see as you increase the number of partitions that it does more closely follow the shape of the graph until you get to something like that on the far right, which is more or less the true shape of the solid of revolution. Here's the formal statement of how to find the volume of revolution using the disk method. We start with a function that is continuous, so it's integrable, and non-negative. That's actually not technically required, but that's what the textbook does. We're going to define R as the region bounded above by the graph of the function, below by the x-axis, on the left by the vertical line, x equal to A, and on the right by the vertical line, x equal B. The region is this area here. And remember, in chapter 5, we found this area by evaluating the definite integral of the function over it. Now, however, we want to find the volume of the solid. We take this and revolve it around it, kind of like a chicken on a rotisserie spit. If you go to the grocery store and you see those chickens going around and around, that's kind of what we're doing. Now, once we have that, the volume of revolution is given by the area of the cylinder times the height of the cylinder dx. That's pi times the function squared dx. And we integrate from A to B. The limits of integration are given by the leftmost position of the rectangles to the rightmost position of the rectangles. The first rectangle, if I were to divide this area, would be way over here at A. And it would be very, very thin. Oops, didn't mean to erase it. And the last rectangle would be here at B. We move from the left to the right, partitioning it into rectangles, which we rotate to create discs. Let's take a look at example 3. In example 3, we have the curve x plus 1 squared. We want to find the volume of revolution produced by revolving a region that's bounded by that function and x equals 0, which is the y-axis, and x equal 2, which is another vertical line, and the x-axis. So we have 4 boundary curves. We have the x-axis, the y-axis, x equal 2, and the function x plus 1 quantity squared. We want to rotate that region around the x-axis. In order to figure out what region you're rotating, you need to look for a region mostly that holds water again. So we're looking for something that is completely bounded by these curves. If it doesn't touch all the curves, then we don't have the right region. So let's go ahead and graph all of those curves in the same color. When you graph them all in the same color, here's our parabola here in red, our vertical line at x equal 2, and the vertical line x equals 0, which is the y-axis. We also have the horizontal line y equals 0, the x-axis. There is a bounded region just to the left of the origin, but it does not touch the boundary line x equal 2. So that cannot be the region that we're revolving. Instead, the region we're revolving has to touch all of them. And it is this gray shaded area you see here. It touches the y-axis here, the parabola here, x equal 2 here, and the x-axis at the bottom. To imagine what it looks like when you revolve it, take this image and draw the reflection of it below the axis of rotation. If it has a positive distance from the axis of rotation, draw the mirror image the same distance but below the axis of rotation. In this case, they touch, and you can see the revolve shape here. Again, sometimes it's helpful to go ahead and connect the sides with small oblong circles, which gives a little bit more of the sense of the 3D nature of the solid. Let's take a look at what it looks like in CalcPlot 3D. In CalcPlot 3D, you can see it looks sort of like this. It does touch the axis of rotation at all points between 0 and 2, which means that it's completely solid on the inside, not hollow. It's shaped sort of like a platter. It's got this circular base right here, and it comes up kind of like this. This is looking at it sort of from behind the bottom, and this is looking at the top, and this is looking at it straight on the edge. And you can see the original region to be revolved and the mirror image of it below that. Let's go ahead and play with it a little bit in CalcPlot 3D, and then we'll go ahead and do the mathematics. You can see here the shape, and again, I'm using a surface of revolution, and I'm using y as a function of x. In this case, the upper curve, if you want to look over here, was the parabola x plus 1 quantity squared, and the lower curve, since it touched the axis of revolution, is the axis of revolution y equals 0. And the region goes from x equals 0 to x equal 2. When we look at this shape, if I revolve it for you a little bit, you can kind of see how it looks sort of like a platter on that side. And I could, in fact, go ahead and revolve it so that it goes up. Well, there you go. You can kind of see it from that edge, and it does look sort of like a platter that's flat on the bottom. Now let's look at it a little bit from the side. When I look at it in this light, if I want to rotate it a little bit, it's kind of hard to see because the colors are very similar. But in fact, you can see the shape of the region that was revolved on the inside in blue. And on the outside, you have this blue-green volume that's there. You can change the color, but I'm not sure if it would also change the color of the other. And it did. So that doesn't help. But we could put on wireframe, and we can look at reversed colors. And in this case, it does pop out a little bit more. You can see the region that we revolved on the inside of the shape. Now let's set up the integral. Coming back to our picture up here, we're going to start on the left side of the region, drawing rectangles. In this case, notice that we always have the parabola on top and the x-axis on the bottom. Because the axis of rotation is horizontal, that makes the strips, which must be perpendicular in the disk method, vertical. And when they're vertical, the narrow end gives the differential dx. My first strip is at x equals 0, and my last strip is at x equal 2. Those give us the limits of integration. Let's go ahead and write down that part already. We're going to go from x equals 0 to x equal 2, and know that x equal is not necessary. Now let's go back to the picture and figure out how to use the formula, area of the circular base times the differential. The area is pi r squared. And if I look at this, it is the length of each rectangle that gives me the radius of the circular disk. So the length of the rectangle is given by the height, or the y value, on the function. And this function was, I believe, x plus 1 quantity squared. So this means that my area becomes pi times the quantity x plus 1 squared, squared again. And then I multiply by the differential dx. This is the height of the cylinder. And this gives me the volume of one disk. And integrating from 0 to 2 gives me the volume of all the disks. From here, we need to square the square, which gives it to the 4th power. This then can be written as the integral from 0 to 2 of pi times x plus 1 to the 4th power dx. Yes, you can multiply it out 4 times, but one, that would take a long time, and two, it's likely you'll make an error somewhere. The better way to approach this one is to use u substitution, where u is x plus 1. The derivative would simply be 1 dx, which we have. Go ahead and pause the video here to work out the integration, and then turn the video back on so you can check whether or not you found the correct volume. So let's compare. Once we have replaced the radius with the function value and squared it, and we got x plus 1 to the 4th, we can make a u substitution that u is x plus 1, so du is dx. Then we replace the limits of integration. When x is 0, u is 1, and when x is 2, u is 3. This allows us to switch only to u and not go back to x. Then we have the integral from 1 to 3 of pi times u to the 4th du. Applying the power rule for integration and substituting the upper and lower limits of integration, we get 242 pi divided by 5 cubic units. This is volume, so it's measured in cubic units. This is about 152 cubic units. Let's take a look now at Calc Plot 3D and see what it estimated the volume to be. I increased the number of washers to the maximum that it will allow, which is 50. And you can tell that it's drawing a much better shape, as you see right here. When I scroll up on the side in the upper band, you can see that it's estimated to be about 152 cubic units. Given that I only have 50 rectangles, this is highly accurate. We've talked about revolving about the x-axis, but we can also revolve about the y-axis. When we revolve about the y-axis, the function is no longer a function of x necessarily. In fact, it may only be a function of y. This means that it will pass the horizontal line test, but it may not pass the vertical line test. This function that you see here is a function of y because it passes the horizontal line test. It is not a function of x because it fails the vertical. It's not a one-to-one function. When we revolve around the y-axis, we simply need the function to be a function of y. In this case, we let g of y be continuous, so it's integrable, and non-negative, though the non-negative we can get around. We define Q as the region bounded on the right by the function g of y, and on the left by the y-axis, below by the line y equals c, and above by the line y equal d. The region Q is given in here, in this space. We want to find the volume of the shape that would be created if we were to take this and revolve it around the y-axis. So I would have to try to draw some mirror image over here. And to be frank, I'm not even sure I can do that. Something like this, where it revolved into this shape that you see here on the inside. Revolving Q about the y-axis will produce something like this shape of a solid. Now, the formula is pretty much identical to the formula for revolving around the x-axis, but instead with respect to y. So instead of integrating from x equal a to x equal b, we integrate from y equals c to y equal d. And the reason is because we're now drawing our rectangles to be perpendicular to the axis of rotation. And that makes the lowest rectangle here at y equals c and the highest rectangle at y equal d. The narrow end of these rectangles gives us the differential, which is dy. And then the formula is still pi times the radius squared. But this time, the radius is given by the x value on that function. In other words, the function itself. Remember that a function of y is written x equals something related to y. So this is actually x equal to g of y. We would take the function of y and square it and multiply by the differential dy and integrate from c to d. Again, the limits of integration are given from the lowest rectangle to the highest rectangle. We would still have a circular disk, and the width of the disk, or the height, is the differential dy. In this graph, you can see the graph of the square root of 4 minus y. Again, this g of y can be replaced with x equals. And when we're revolving, this distance right here, which is the radius, is the x value, which is also the root of 4 minus y. And when you rotate it around that vertical axis, you get the disk again, but this time the disk is oriented horizontally. And they'll be stacked up like this. Let's take a look at an example of revolving about the y-axis. In example 4, we want to take the region that's bounded by the graph of e to the x, the exponential, which you see here, the graph y equals 3, which is a horizontal line, and the y-axis, which is just a vertical line, x equals 0. If we highlight those three graphs, we're looking for the region that is trapped by all of those curves, the y-axis, e to the x, and y equals 3. The purple shaded region is the region that holds water. It's trapped. And we want to rotate it around the y-axis, not the x. In order to rotate around the y, we will have to make our strips be horizontal, perpendicular. And that makes the differential dy. This graph right here then will have to be written x equal a function of y. You can see down here the pictures coming from Calc Plot 3D. When we look at these, you can see that I've taken the purple space here and I've divided it into a number of strips. They're all oriented horizontally, and then I'm going to rotate around the y-axis. In this picture, you can see one representative rectangle that's been rotated. And here they're all rotated. And here I allowed the number of partitions to increase. And you get a better idea of what it looks like. Now, this region does touch the axis of rotation all the way along between C and D. And that means it will be solid on the inside. In this case, we need to rewrite that function. To revolve around the y-axis or another vertical line, you have to be integrating with respect to y. So your function has to be written x equals something with y in it. We were given y equal e to the x. Well, I can rewrite this in logarithmic form as the natural log of y equal to x. So now I have my g of y, which is natural log of y. The integration will be from 1 to 3. And the reason is because the lowest strip that we can see here in our picture is at 1, and the highest strip is when y equals 3. The location of the strips gives you the limits of integration. So we will be integrating from 1 to 3. And again, these are y values. Then we write pi, and then we take our function of y and we square it, multiply by pi, and the differential dy. We do not have the techniques in order to actually integrate this one. It requires a technique called integration by parts, which you will learn in Calculus 2. But we can at least go ahead and write down what the integral is. Now, again, I can't emphasize enough how important it is that you know what the axis of revolution is and that you sketch out what the solid should look like. It makes a huge difference which one you're going to revolve around. Let's take a look at this particular one now. In order to get this entered correctly, I had to choose down here x as a function of y, x equal f of y, instead of y equal f of x. This will force it to use the method of disks when we're going around the y-axis. Then instead of asking me for the graph above and the graph below, it asks for the graph on the right and the graph on the left. The graph on the right is given by the function e to the x, but we have to rewrite it as x equal the natural log of y. So on the right, I have natural log of y. On the left side is simply the y-axis, x equals 0. So I write x equals 0. We're revolving around the y-axis, x equals 0, and we're going from y equal 1 to 3. You can see the partitions here. Let's go ahead and revolve them. First, we'll show a representative, and we'll revolve it. For some reason, I think it was already revolved. Okay, let's go ahead and tilt it down. Oops, I always forget. I need to be over here. If I tilt it down, you can see that disk appearing. Now let's go ahead and revolve all of the disks. If I revolve them all, I can get this solid. And if I increase the number of shells, I can get very close to the actual solid. And again, it will give me what it thinks the volume of it is. And I can rotate this in different directions to see sort of what it looks like. It's solid on top and circular, and it comes down to a point. This is what it looks like when you revolve that region around the y-axis. Let's now take the same region, but revolve around the x-axis. If we take that region and revolve around the x, then we have to draw our strips vertically so that they're perpendicular to the horizontal x-axis. This makes the differential dx. So at the bottom, I need to choose y as a function of x. Then the top graph becomes, instead of right left, becomes above and below. The upper end of the strips touches y equal 3, the constant horizontal line, and the bottom of the strips is touching the function y equal e to the x. Then I have to know, for example, what the x coordinate of that point right there is. When is e to the x equal to 3? Well, when x is the natural log of 3. So I integrate from 0 to the natural log of 3. Let's look at what this one looks like when we revolve. Notice that it does not touch the axis of rotation. So when I revolve, I have something that is hollow on the inside. And if I increase the number of washers and shells, I can see that I get, well, a sort of a disc. It's gotten kind of dark, so I'll take the edges off and see if it can give me a slightly better picture. When I look at this, it's sort of, well, slopes in, sort of like an arena, where it's coming down like this and has a, well, an open space on the floor. So these sides are sloping up in the way that the e to the x was curving around. Again, when you look at a function, you must know which way it revolves. This is what it looks like revolved around the y-axis, and this is what it looks like revolved around the x-axis. We'll be working this problem a little bit later on as well. We're going to end our discussion of finding the volume of revolution using the disk method here. In the next video, we're going to take an application of volumes of revolution by disks when we look at using the washer method instead for regions to be revolved that do not touch the axis of revolution. See you for the next video.